Hello, my name is Donghao. Today I'm going to introduce a topic about the derivative. First, I want to introduce what is a derivative. The derivative is a function, and the derivative is the slope of the tangent line at that point. And the derivative also represents the rate of the change of a function. So let's introduce the tangent line. Because the derivative is the slope of the tangent line, so tangent line is very important for the derivative. The tangent line is the intercept at one point along the original function, and also the slope of the tangent line is the slope of the original function at the point of intersection. Next, I'm going to introduce the secant line. The secant line is very similar to the tangent line. It just has like 2 points on the graph intersecting at each of them. Usually, people calculate slope with the y2 minus y1 over x2 minus s1, but we just rewrite the y2 and the y1 and the s2, s1 into fa and fx. So the new slope for the secant line will be fa minus fx over a minus x. And this also represents the average slope between the points x, fx, and a, fa. Now let's move the points x and closer together to see how the secant line transforms. We move the line closer to the secant line. So the new slope of the secant line will be fa2 minus fx divided by the a2 minus x, because we move the point, so there will be a new y value. And now we represent the y value as fa. This represents the average slope between the point x, fx, and a2, fa2. Now the slope of the secant line is closer to our tangent. So the next graph will be the secant line in a closer look. As we move the 2 points closer and closer together on the x-axis, homing in one on the point intersected by the tangent in each direction, we will approach a perfect tangent line. So let's refer back to our average slope between 2 points, working with average slope. The average slope will equal to fa minus fx over a minus x. We noted that as a and x get closer together, the slope of the secant line, represented by the two, gets closer to the tangent line. Therefore, getting closer to the actual slope of the function at x, what will happen if we took the limit of this expression at the distance approach 0?
So before taking our limit, we need to find a proper definition for what slope really means. Our equation comes directly from the slope of a secant line, where rise over run is determined by our x's and y's of the function. Our difference in x, being a minus x, is represented as the letter h, and it stands for a small difference in x as we approach a certain limit. Limits typically take the form of having some variable approach any given value, where in this case we have h approach 0 because as our x's get arbitrarily close, the function of our secant line will closely resemble a tangent line at a given point x. So the limit form of differentiation tells us that the f prime of x is equivalent to the limit as h approaches 0 of our function x plus h minus the f of x, all divided by h. In the case of y being a function of x, we represent the limit definition of the derivative with many notations, including dy dx, df dx, or simply the f prime of it, depending on how you write your functions. Let's have a common example for taking the first derivative of a function. Let's allow our function y to be equivalent to x squared. When we substitute our function into the expression, the derivative according to the limit definition will be the limit as h approaches 0 of x plus h squared minus h squared over h. Here we see that we must expand our expression of dy dx in order to help cancel out some of our function to allow h approach 0. As of now, we may not simply compute our derivative because h is in the denominator, and as h approaches 0, our function becomes undefined. Therefore, we manipulate the expression in such a way that we arrive at a point where we may cancel out an h. In this case, we expand our square product of x plus h squared minus x squared, so that our numerator shows to be x squared plus 2hx plus h squared minus x squared, all over h. From here we see that the x squareds cancel, and we are left with 2hx plus h squared over h as our limit of h approaches 0. As we can see, we can take out a single h from the numerator. We can now see that the h's cancel from the numerator and denominator, just leaving the limit as h approaches 0 being 2x plus h, which will leave us simply with the derivative dy dx equaling 2x. So what does this mean? Well, we stated earlier that the derivative of a function is the rate of change or slope of the function. We saw that the derivative of x squared is equivalent to 2x. We can use the derivative to find the slope of a function at a point. In this case, let's find the slope when x is equal to 4. When x is 4, the slope of our function will be equivalent to 2x. And since x is 4, we can resolve that the slope at x equals 4 is equivalent to 8. The slope of a function is very important and can be applied to many aspects in life. When we express a position function, we take its derivative, we are accounting for the velocity of the function at any given point in time. Likewise, were we to take the derivative of a velocity function, we would create a function describing acceleration.
When we find the derivative of a function, we often do not actually use the limit definition presented previously. Instead, we use a set of collected rules to determine the derivative of a function. We will introduce some common identities on the next page, then look at some of the more complicated differentiation rules. These are some commonly found identities when finding derivatives of functions. The derivative of any constant c is 0. The derivative of the natural log of x is 1 over x. The derivative of e to the x is e to the x. The derivative of any constant a to the x is a to the x times the natural log of a. The derivative of sine of x is cosine of x. The derivative of cosine of x is the negative sine of x. The derivative of a sum or difference of two functions is the sum or difference of the derivatives of the functions. For example, if h of x equals the natural log of x plus e to the x, the derivative is the derivative of ln of x plus the derivative of e to the x, which is 1 over x plus e to the x. We apply this similarly in functions that involve sums or differences of any kind. The derivative of sine of x minus 4 to the x would be cosine of x minus 4 to the x times the natural log of 4. The first of these rules is the power rule. When differentiating a function involving an independent variable x raised to a power n, we multiply the expression by n and subtract 1 from the power. The derivative of the function x to the fourth will be 4 times x to the third.
Next up is the product rule. When we differentiate a function that is the product of other functions, we follow this special rule. If we have h of x equal to two functions, f of x and times g of x, then we first take the derivative of f of x and multiply it by g of x, and then we add f of x multiplied by the derivative of g of x. For example, if we have the function x squared times the ln of x, we would first take the derivative of x squared, which is 2x, and then multiply it by the other part of our function, ln of x. We would then add, and we would have x squared, the original first part of the function, times the derivative of our second part, 1 over x. This makes our final derivative 2x times the ln of x plus x squared times 1 over x. Then we have the quotient rule. When we differentiate the quotient of two functions, such as h of x equals f of x over g of x, we operate similarly to the product rule. We first differentiate f of x and multiply it by g of x, and then instead of adding, we subtract f of x multiplied by the derivative of g of x. And then, finally, we divide the entire expression by g of x squared. So let's look at an example. E to the x over x squared. If we differentiate this, we need to first differentiate the top part of our equation. The derivative of e to the x is simply e to the x. We then multiply it by the bottom part of our function, x squared. Then we subtract the top part of our function, e to the x, multiplied by the derivative of the bottom part of the function. That is the derivative of x squared, which is 2x.
We then finally divide the entire expression by x squared squared, remembering that whenever we raise a power to another power, we simply multiply the two together. We can further simplify this expression into e to the x times the quantity x minus 2 all over x cubed. And last up, we have the chain rule. The chain rule is perhaps one of the most forgotten rules in all of differentiation. It's a most common mistake whenever students are taking the derivative of any sort of function. It states that when you take the derivative of a composite function, you must first take the derivative of the outside function and multiply it by the derivative of the inside function. That is to say, if we had sine of x squared, our sine would be the outside function, while x squared is the inside function. So we first take the derivative of the outside. We know that the derivative of sine is cosine, so the sine of x squared becomes cosine of x squared. But we're not done. We still have to multiply by the derivative of the inside function, that is, the derivative of x squared. So our final answer is cosine of x squared times 2x. That wraps up our introduction to the first derivative and its rules. We hope you found this material useful, and good luck on your further mathematical journeys.